Okay, in this video I want to discuss the orthogonal complement of a subspace. Okay, suppose that W is a subspace of R to the n. Okay, the orthogonal complement of W in R to the n, written this way, W with what? A superscript up here being this little perpendicular sign, okay, which is what? Like an upside down T. Remember that symbol from geometry? Okay, that means perpendicular. That's the Latin. In Greek, what is perpendicular? Orthogonal. Okay. Anyways, so the orthogonal complement of W in R to the nth, written this way, is the set of all vectors in R to the n such that x bar dotted with W is equal to 0 for all W in W bar in the subspace W. In other words, it's the set of all vectors which are what? Orthogonal to every vector in W, in that subspace W, okay? So it's a set of all vectors that are orthogonal to every single vector in W, okay? So that's what we have. I've sort of written it succinctly here. Okay, there it is. Okay. Now this is an exercise for you. If W is the span of these vectors, okay, just think of this as a basis maybe, then W perp, okay, or the orthogonal complement, is the set of all vectors in Rn orthogonal to each of these vectors in the spanning set. That would be sufficient, okay? Does that make sense? That's a little exercise for you. It's actually sufficient, I'm saying, to consider all vectors that are orthogonal to every single one of these. If that's good enough to talk about being orthogonal to every single vector in the subspace W. Okay? All right, that's an easy proof. Let's talk about this. W perp here, okay, is a subspace of R to the n. Okay? How would we do that? There's different ways we've approached this. One time we just talked about saying it's what? Closed under linear combinations. The lengthier way, slightly lengthier, is to go ahead and consider the following three. 0 is actually in W perp, right? Okay? In the orthogonal complement. Why? Well, the 0 vector dotted with any W is going to give you, oops, that shouldn't have a bar on it. That should be just what? 0, right? The dot product is going to be 0 for all W bar in W. In fact, all W everywhere. But there it is, okay? So definitely W perp contains what? The 0 vector, okay? Now that's the first thing we would need for a subspace. What's the second thing? We need closure under addition, whatever order you like to do these in. Suppose x1 and x2 are elements of W perp here. Then what? Then if I go x1 plus x2 and then dot that with W, where W is an arbitrary, W bar is an arbitrary vector in the subspace W, then I could use the distributive property and go what? x1.w plus x2.w. But these are going to be what? These are going to be 0. Both of those are going to have the value of 0, so their sum is going to be 0, and that's going to be true for all W bar in the sample space W, or subspace W. Keep saying sample space like it's stats or something. Subspace. Okay? So then what does this mean then? This means it's going to be closed under what? Sums. Okay? One last thing we want to check here. A is an element of the real numbers, and x bar is an element of W perp here. We want to know if this is actually closed under scalar multiples, okay? If I go A times x bar as a single vector and dot it with W, then I could bring that what? A on the outside of that dot product, because I have a scalar associative property. X dotted with W is going to be always 0. Okay, A times 0 is 0. This is going to hold for all W in all W bar in the sample space W, or subspace W, isn't it? Okay, so that means it's also closed under scalar multiples. Okay, so we definitely have that this is a subspace of Rn. Later on, we're actually going to show here that our whole space, like Rn, can be written this way. It's the direct sum of W and this is a special sum here. Well, it's not really a special sum, but it indicates that the only subspace in common between these two sets is the zero subspace. In other words, the zero vector itself. Okay? We can actually get the whole space by adding W plus W perp. Okay? You don't really have to worry about that right now. Let's take a quick problem here. Suppose W, my subspace in R cubed, is going to be the span of these two vectors, 1, 1, negative 2, 2, 0, 1. Find W perp. Find some way to characterize it besides just saying this. Suppose I say X bar is this one, X1, X2, X3. Here I've got, just wrote it compactly, running out of room here. So I used the transpose here. It's really a column vector. Okay, this is going to be an element of W perp. I should have here. See, little errors. If and only if the following holds. Well, remember that this vector dotted with these should be 0. Okay, this vector dotted with these should both be 0, right? Okay, so let's go ahead and do that. Or if you write that out, the dot product, with the first vector there, that would mean x1 plus x2 minus 2x3 has to be 0. And when we dot it with 2, 0, 1, that would be what? 2x1 plus 0x2 plus 1x3. That's got to be 0 also, indicating that they're what? Orthogonal there. Okay? So dot products are 0. Now we could just write that as a system of equations, right? x1, x2, x3. Okay, and I've done that. Then we just go ahead and use Gaussian elimination on that. And I've written up here x1, x2, x3. You can see that the rank of this is 2. Okay, but there's 3 columns of unknowns here. Therefore, we're going to have what? 1 free parameter here. Okay, solving each of these equations in terms of the single free parameter, x1 would be negative a half times x3. x2 would be what? 5 halves times x3. And x3 is a free parameter, so I just say x3 is x3. So in fact, x is going to be what? The scalar multiples of what? Negative a half, 5 halves, and 1. So that W perp is actually the span of this vector, negative 1 half, 5 halves, and 1. Notice that this is also the span of what? Negative 1, 5, and 2. Make it just a little bit easier by factoring out a 1 half there. Okay? Now, you might do this just real quickly, just as a double check. I've got negative 1, 5, 2. Take the dot product of that with both of these original basis vectors, and I think you end up getting 0 in both cases. In fact, I know you do. Okay, so it's actually working here. Okay, so you should be able to work problems of this kind in various forms. Go ahead and look at those problems involving this stuff. Okay, I hope you understood that then.